Today we want to finish up writing triple integrals in spherical coordinates. Remember, the issue that we have is we want to build one factor of our integral as dv. So we have these factors of the integral is a dv, which is a small chunk of volume that we model with length, width, height. So dx, dy, dz, a small change in x, a small change in y, and a small change in z. In rectangular coordinates, dx, dy, and dz are all length. So dv is a volume. What we want is a length. Dy is also a length. And dz is also a length. And so that allows dv to be a volume. So I've got meters times meters. That gives me cubic meters. That's a volume. What we saw in polar coordinates, and so also in cylindrical coordinates, is that theta is not a length. Theta is not going to be measured, d theta is not measured in meters. But if we have some small change in theta, this is a huge change in theta, but if we have some small change in theta, we approximate the using the arc length. And so we trade r to turn d theta into a length. Dr is a length, no problem. But to turn d theta into a length, we multiply by r. That's just how far we are away from the origin in the xy plane. And in cylindrical coordinates, that's the only one that we have to change. In spherical coordinates, we need to turn d theta and d phi into length. Rho is a distance, so that's just going to, the d rho is going to be a length, so that's no problem. D theta needs to turn into a length, but the way we did in cylindrical coordinates isn't going to work because we had r times d theta. But there's no r here in spherical coordinates. We just have rho. For d phi, phi is measured from the positive z-axis, and rho is just the distance from the origin. So we can multiply rho times d phi to turn d phi into a length. So rho is one of the legs that's attached to phi. So some small change in phi, we're going to get an arc length that's rho units away from the origin. So rho d phi will turn d phi into a length. D rho is already a length. D phi can be turned into a length just by multiplying by rho. But that still leaves d theta to be turned into a length. Here's what we want to remember. Here's what we want to notice. In cylindrical coordinates, we turn d theta into a length by multiplying by r. We can't use r, but we do want that quantity. So notice that r from the origin to the point in the xy plane directly below the point xyz, or the point r theta z, or rho theta phi, that this distance up here is also r. Now I'm going to pull out this right triangle with rho as the hypotenuse, r as one leg, and z as the other leg. So let's pull out that right triangle. So here is the origin down here at the bottom. Up here at the top is Z. Rho is going to be the hypotenuse. And even though we don't, in cylindrical coordinates, the other leg of this triangle is going to be R. So I can't say rho times or R times d theta, but I can write R in terms of rho and phi. So we can't write R d theta. We need to write R in terms of rho and phi. So R the sine of phi will be R over rho, because sine of an angle is opposite over hypotenuse. So we just need to solve for R, and that means multiplying by rho. So R is equal to rho times the sine of phi. The reason that we want to do this is that we turn theta into a length by multiplying by R. But we don't have R. We only have rho, theta, and phi. We have to write R in terms of rho and phi. So if R is rho times sine of phi, that's how we'll turn phi, d phi into a length. We'll multiply by rho sine phi d theta. Now that d theta is a length. So when we're looking at triple integrals in spherical coordinates, that's where that factor of rho squared times sine of phi comes from. Those factors are there because we need to turn d phi and d theta into length. So our triple integral in rectangular coordinates will just be dx, dy, dz. Our triple integral in cylindrical coordinates we'll need an r dr d theta dz. That r goes with the d theta to make length. Or in spherical coordinates, we'll need rho squared times the sine of phi. D rho is length. We need rho sine phi to turn d theta into a length. And we just need another copy of rho to turn d phi into a length. So what we want to notice is that we're integrating over some solid, a function of 3 variables. This r is part of the dv. This rho squared sine of phi is part of the dv. So over here, these are our expressions for dv. Those are all expressions for dv. So we're taking, as far as the slices go, a small change in phi. So we've got the z-axis up here. The small change in phi is down here at, let's see. Phi is going to be this angle in this angle, and rho is going to be that length. The D phi is going to be some small change in phi. So we're making an arc and what we want is to approximate an arc length over D phi. We're going to use this arc length as the length, the one of the sides of this rectangular solid. It's curved, but if D phi is small enough, it's not curved that much. The smaller the angle is, the closer the arc length will be to flat. D rho is a change in length. So D rho is a change in length. And then coming out of the page or going into the page, that's where we would see a change in angle as we rotate up out of the page. I want to go up out of the page because I can't phase my pen into my surface. But that rotation out of the page will be based on a change in angle theta down here. And for that, we can just do the same thing that we did with cylindrical coordinates and polar coordinates. How far is that point away from the origin, but only in the XY plane? That distance is called r in polar and cylindrical coordinates, but it's going to be rho sine phi in spherical coordinates. So one of the things that we know is that if we integrate over, if we integrate the function 1 over an interval, we get the length of the interval. If we integrate the function 1 over a region, we get the area of the region. And if we integrate the function 1 over a solid, we should get the volume of the solid. Let's find out. So for an example, let's let W be a sphere of radius 3 centered at the origin. We know the volume of this sphere is 4/3 times pi times 3 cubed. Shouldn't use 3. I'm going to use a bigger sphere because I don't want things to cancel out. I don't know why. It's very clear. which 3 is which. But there's that 3 from the 4/3, so I'm just going to push the radius out to 5. So people don't just start canceling one factor of the radius for weird reasons. So we know that the volume of this sphere is 4/3 times pi times 5 cubed. So 125, what's 125 times 4? 250, 500. 500 pi over 3. So finding the volume of the sphere is not the point. Setting up a triple integral and verifying that triple integral gives us the thing that we expect. That's the point. So we have a sphere of radius 5 centered at the origin. So I'm just going to draw an attempt at a sphere. And I want to put the axes in. I'm going to put the rectangular ones in, even though we're going to do this. Oops. Now, we got to pick a coordinate system to integrate this function. Since, yikes. For some reason, I really want to, apparently subconsciously, I really want to switch up my axes, but that's crazy. So we could do this in any set of coordinates that we want, but since the thing that we're trying to measure is a sphere, I think spherical coordinates might be best. We're going to integrate the function we're going to integrate the function 1 over we're going to integrate the function 1 over this sphere dv, and that should give us the volume of the sphere, or in general, the volume of W. I don't know if this is a more coffee problem or a less coffee problem, but I know what solution I can apply. So what we need to do is describe, and we're going to use spherical coordinates. So what we need to do is describe the sphere in a way that the integral will understand. What values of rho, what values of theta, and what values of phi. So the nice thing, since we have a sphere, we're going to use spherical coordinates. So the tricky thing is that we can't just integrate d rho, d theta, d phi, because d theta and d phi are not length. So I'm going to put on the outside rho. And I'm going to integrate over all the radii. So rho should go from 0 to 5, because that's the radius of a sphere. I'm looking at everything from the origin to 5 units away from the origin. My theta, I want to go all the way around, because I want the theta is going to be from the positive x-axis, and I want the whole sphere. So we're going all the way around. So theta should go from 0 to 2 pi, because we want to integrate theta all the way around the sphere. For the angle phi, we're measured from the top, the z-axis to the negative z-axis. So from the top all the way to the bottom. We want to stop there because we've got theta going all the way around. We only need phi to go from 0 to pi. So phi will go from 0 to pi. Now in this case, it looks like we're integrating d phi, d theta, d rho. This is the order that we're integrating. But we can't just integrate the function 1. I've got this huge conspicuous space between 1 and the other part of my dv. That's where the rho squared sine of phi is going to go. I need one factor of rho to turn d phi into a length. I need rho sine of phi to turn d theta into a length. So here I'm going to have the rho squared sine phi. From a mechanical standpoint, you just have to remember that your triple integrals in spherical coordinates are going to need a factor of rho squared sine of phi. It's helpful to keep in mind why we have that. Helps us understand where things come from. When we understand where the things come from, then we'll have a harder time forgetting where things come from, or actually forgetting what they are. So I need rho sine phi to turn d theta into a length. I need another copy of rho to turn d phi into a length. Now, this is the function that we're integrating. First, we're integrating d phi. Rho squared is just a constant. So the integral of sine of phi d phi is negative cosine. So I have negative cosine phi evaluated from 0 to pi. I still have rho squared. I've integrated d phi. I still have my d theta integral to go. And I still have my d rho integral to go. My d theta integral is going to go from 0 to 2 pi. And my d rho integral is going to go from 0 to 5. So I need cosine of pi minus the cosine at 0. So I have minus rho squared cosine of pi minus a minus rho squared cosine of 0. Cosine of 0 is 1. Cosine of pi is negative 1. So it looks like we're going to have 2 rho squared. You should probably check my algebra and my trigonometry. You know that I'm not very good at algebra, arithmetic, or trigonometry. So we're integrating from 0 to 5, from 0 to 2 pi, just the function 2 rho squared. From 0 to 5, d rho, and from 0 to 2 pi, d theta. Now let's integrate d theta. 2 rho squared is all constant. Still integrating from 0 to 5, but the integral of 2 rho squared with respect to theta is just 2 rho squared times theta. And then we'll evaluate it from 0 to 2 pi. I'm still going to take the result and integrate from 0 to 5 d rho. We're integrating phi from 0 to pi because we're measuring phi from the positive z-axis. So phi equals 0 is up on the positive z-axis, and I want to integrate all the way down to the negative z-axis. If I go past pi on d rho, I'm going to start counting stuff twice because I'm integrating theta from 0 all the way around to 2 pi. So 0 to 2 pi is giving us this whole circle all the way around the xy axis. So to get the top and the bottom, if I have, say, this theta here, theta at pi over 4, when we integrate the pi over 4 all the way around the circle, we're getting both sides. That's why I don't want to integrate. That's why I only want to integrate from 0 to pi, not 0 to 2 pi. So we're only going to integrate phi from 0 to pi. Whereas theta, we need to integrate all the way around. We had to pick one to be half. That's really what it comes down to. One of them had to be half. I could integrate from, say, 0 to, I don't want to get into that discussion. We had to pick one of them to be smaller. Otherwise, we'd count things double. So we're going to plug in 2 pi and we're going to plug in 0 into the theta. So we'll have 2 rho squared times 2 pi minus 2 rho squared times 0. So this is going to be 0. We're going to have 4 rho squared pi, 4 pi rho squared. And now we really see, this is why I wanted the d rho to show up last, because now we can easily see how this is going to turn into our 4/3. We're going to integrate from 0 to 5. Our function 4 pi rho squared, and this is our last integral, d rho. Now we integrate 4 pi rho squared with respect to rho. So we'll have 4/3 pi times rho cubed evaluated from 0 to 5. Emperor style, just as we had foreseen. Now, once again, the point was not to figure out the volume of the sphere. We already knew that. And we've known this for thousands of years. That wasn't the point. The point is, take these techniques and apply them to something familiar so that we can apply them to new things and have more confidence that they'll work. Also notice that the calculus part, where we add one of the exponent, divide by the new exponent, the mechanical bits of the calculus, for this problem at least, were very simple. And also not the point of the problem. The point of the problem, as is the point with all math problems, is setting up the problem so that the math we learned can apply to it. This is why all the problems in algebra seem so contrived. That's because all the problems in algebra are so contrived, because they're designed to make you practice algebra things. Similarly, what we're doing right here. The point is not to find the volume of a sphere. We have a formula for that. But formulas are boring, and they'll betray us, and we won't know where they come from. And as soon as we stop knowing where things come from or how they work, we start becoming easily manipulated. Don't believe me? Put your uncle in front of YouTube and just let it run on autoplay. And then in a couple of days, he will be radicalized. And we know that that's going to happen because we know at least the basics of how the algorithm works. Oh, you like that? How about this? I think it depends on what your uncle starts on. It might be that he's radicalized because a radicalized flat earth believer, but who knows? Yeah, UFO videos. Or moon landing conspiracy. Because if there's one thing that we know about humanity, is that if you have a group of thousands of people, it's totally easy for them to keep a secret. That's a perfectly rational decision. Wait, that doesn't seem reasonable at all. I mean, think about your friends group. Is there someone in your friends group who you would not tell a secret to because the rest of your friends would know? Now think about the size of your friends group compared to the number of people working, say, at NASA for the moon landing. And then try to convince me that they all keep it a secret. I'm just trying to Occam's razor this thing here. You know what I mean? Don't let YouTube radicalize you. Especially if you're going to let YouTube radicalize a big chunk of your population. And then when you turn to YouTube and say, hey, what the heck, YouTube? And then YouTube just kind of like shrugs. It's like, oh, did I do that? And you're like, well, yeah, you did that. And you know you did that. It's like, oh, we didn't expect that to happen. Anyway, what are we talking about? The point wasn't coming up with 500 pi over 3. We already knew that. We wanted to verify that this line of thinking will work in at least one case. And then we can start applying this to other things. A lot of times students will be asking me, it's like, oh, hey, man, when am I ever going to use this in my real life? It's like, oh, I have no idea. It's impossible for me to know that. But for another glib answer with that, it's like, I don't know. You tell me, what are you going to be doing with this kind of information? Knowledge is only power if you wield it. How are you going to wield your power? Historically, we're going to take the best and brightest minds of artificial intelligence, and we're going to try to put them on the very important problem of making people click more things. But I don't know, maybe we'll get something out of it. All right, that's going to do it for today. Keep thinking about where this, always keep thinking about where this rho squared sine phi comes from. Why does it have to be there? Where do we get it? Remember what all the symbols represent. W is the set of x, y, and z that we're plugging into the function and multiplying by this dv, and then just adding up all those values. We're just trying to tell the integral what values of the variables to plug into the function. So think about what we're doing with this integral, and that will help reinforce where these things come from, because it's not just random. As much as students like to think we do this just to make your life more difficult and miserable, this isn't about you. Any questions? Comments? Deep thoughts? All right, you're not the main character, and neither am I. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day. Thanks for playing.